If you're getting ready for a machine learning interview, you know the deal. Probability and stats, they aren't just one topic on a checklist, they are the absolute foundation of everything. So today, we're not just going to review the concepts. Nope, we're going to put you in the hot seat. So picture this. You're in the chair, you've already passed the first screening call, and now it's time for the real deal, the technical round. For the next few minutes, I'm your interviewer. You ready? All right, don't be nervous. I'm really just here to see how you think, especially about things like uncertainty and data. We'll kick things off with the absolute fundamentals. Okay, so my first question for you is about the bedrock of this entire field. Can you walk me through the fundamental axioms of probability? Yep, that's exactly what I'm looking for. You'd want to name these 3 core rules. First, non-negativity. Super simple, right? The probability of anything happening can't be negative. Second, unitarity. This just means the probability of all possible outcomes has to add up to 100%. And finally, additivity. For events that can't happen at the same time, the probability of one or the other happening is just the sum of their individual probabilities. So here's why that matters. Knowing these axioms shows your interviewer that you get it, that probability isn't just some vague idea, it's a solid, rigorous mathematical system. It shows you respect the fundamentals.
Good. Okay, let's build on that foundation. A really common follow-up question is about how we update our beliefs when we get new information. So tell me, what's the relationship between conditional probability and independence?
At the heart of it all is this idea of P of A given B, the probability of event A happening given that we already know event B has happened. Look, it's more than a formula. It's the engine for how we update our point of view when new evidence comes in.
Now, this brings us to a huge interview pitfall. So many people mix up independence with mutual exclusivity. For independent events, like rolling 2 dice, knowing one outcome tells you 0 about the other. But for mutually exclusive events, like a coin flip, if you get heads, the chance of getting tails just drop to 0. They are completely dependent on each other. Nailing this distinction, that's a big win in an interview.
Excellent. That is exactly the kind of clarity I'm looking for. Okay, now let's see how that idea builds into what is, well, you could argue it's the most important theorem in all of probabilistic machine learning. So my next question for you is a 2-parter. First, can you just state Bayes' theorem for me? And then, and this is the important part, can you tell me what it actually means in a machine learning context? And there it is. The magic of this formula is that it lets us flip a conditional probability. We figure out our posterior, our new updated belief, by taking the likelihood, how likely our evidence is given our theory, and multiplying it by our prior, what we believed in the first place. Then we just divide by the evidence to make sure it all adds up. It's really just a beautiful mathematical way to learn from data. And a spam filter is the perfect example of its power. Let's say our hypothesis is, this email is spam. We have some initial or prior belief about that. Then we see the evidence. The word lottery is in the email. Bayes' theorem lets us combine our prior belief with the likelihood of seeing lottery in spam to calculate a new, updated posterior probability that this specific email is spam. This is the core logic behind so many ML systems. Very strong. You've clearly got a handle on how we update beliefs. So now, let's switch gears and talk about the data itself. A huge part of machine learning is, of course, modeling the underlying shape of our data. Let's talk about a practical situation. Imagine I just hand you a new dataset. What's your thought process for deciding whether to model a feature using, say, a normal distribution versus a Poisson distribution? How do you make that call? A great answer shows me you have a mental map that looks something like this. You'd explain that the normal distribution is your go-to for continuous data that's kind of symmetric, like the errors in a regression model. But then you'd pivot and say Poisson is for modeling counts of events, like how many people visit a website in an hour. And if you wanted to model the time between those visits, well, that's a textbook case for the exponential distribution. Knowing the shape of your data is half the battle. And honestly, that's the real takeaway. You can't just throw an algorithm at a problem and hope for the best. Choosing a model whose built-in assumptions actually match the real-world nature of your data, that is absolutely fundamental to getting results you can trust. All right, we've covered the rules, updating our beliefs, and modeling data. For the final part of our interview, let's zoom out to the really big picture. I want to talk about the 2 grand laws that in a lot of ways are the reason machine learning even works in the first place. So first, the law of large numbers. You can think of it as a guarantee.
It basically says that if you collect enough data, the average of your sample will get closer and closer and closer to the true average of the entire population you care about.
This right here, this is the mathematical reason we're always chanting more data is better. As our training set gets bigger, we get more confident that its performance is a good estimate for how the model will do out in the real world. But, and this is a huge but, notice the word quality. The law doesn't help you one bit if your data is biased or just plain wrong.
And last but not least, its amazing partner, the central limit theorem. Honestly, this one feels a little bit like magic. It says that if you take a bunch of big samples from any population, it doesn't matter how weird its original shape is, the distribution of the means of those samples will start to look like a normal bell curve.
And this is just so incredibly useful. It's the reason we can run an A/B test, find the average conversion rate for each group, and then use standard statistical tests, which assume that nice normal bell curve, to see if the difference is real. The CLT is the engine that powers so much of how we make confident decisions.
Okay, let's stop there. That concludes our technical screen. Seriously, you did an excellent job. You walked through those concepts with real clarity and depth. It was a pleasure speaking with you. And that brings our little interview prep session to a close. We've hit the foundational axioms, the mighty Bayes theorem, key data distributions, and the two big laws that make it all possible. So now, the only question left for you is, which of these concepts are you going to master before your next interview? Good luck, and thanks for joining me.